opposite charge. So that why is shifted. So over there, this energy gap is actually the electron spin flipping. Okay, it is the electron spin flipping, or in other words, what we talk about, ESR or EPR, electron spin resonance or electron paramagnetic resonance. So over there, to make sure that this resonance happen, you have to give the appropriate energy gap between them, and that is coming from the microwave. Okay, and it is connected to the mass, but not directly connected to mass. It is not like connected to mass as it is in a kinetic system. It's a little bit different because it's a quantum mechanical system. So you look into that. So you probably heard about something called Bohr magneton in the EPR, which actually is EH by 4 pi MC and all those terms. So over there, this full term actually controls what will be the energy gap. So over there, mass is one of the part over there. There are other integral property of the electron or proton is also connected to that. Okay, so in this aspect, it is actually happening again in the microwave region. Okay, so it is actually just nothing but a coincidence that the energy required to change the energy gap between different rotational states of an electron and the electron spin is actually in the same region. So they are not directly connected in that such way, but they can be excited using the same energy region, and that is the microwave region. And microwave region falls around 10 to the power minus 4 electron volts. So it is 10 times, at least 10 times higher in energy compared to the radio frequency. Any one of you ever used a microwave, what should I say, microwave energy producer system? Have you ever seen any system which actually creates microwave?
Microwave bin, sir.
Yeah, microwave itself. So can you tell me why the microwave heats the things up?
Sir, the water molecules in the food sample are actually excited, and when they relax back, they release heat, heating the food item.
So which states we are actually exciting?
Rotational.
Okay, we are exciting rotational spectra. That is true. So it is actually going from ground state of the rotational state to the higher state of the rotational state. But when it is coming back, why it is not losing the energy as a frequency itself? Why it is actually leaving it as a heat energy? So keep that thought in mind. We'll come back to that. Why it is losing the energy as a heat energy, not as a radiative energy. Why it is creating a non-radiative factor. We'll come back into that. So this is just to give you an idea that you know part of it. Actually, you have used that probably all of your home nowadays. A microwave said generally when you try to heat the food, we generally try to sprinkle some water on that, because this is the water or the liquidy part actually goes to the higher excited state of rotational energy, and then it relaxes back as heat energy. And that is the heat which actually heats up the whole system. Okay, we'll come back to that later. So now coming to the next one. The next one we can use is infrared region. And what is the spectroscopy? We can do it over here. Generally, we talk about FTIR, Fourier transform infrared spectroscopy. But in general, it is nothing but the vibrational spectroscopy. Okay, so it is the vibration of a bond of a molecule, especially through the bonds. And over there, it takes more energy to distort the electron density between two bonds rather than rotating. So that's why you need more energy. And IR energy generally falls in the range of 0.1 electron volt. So you can see it is huge difference, almost 100 times more different compared to 100 to 1,000 times more different compared to microwave. So it is much more stronger energy in the IR. Okay, and it actually excited the ground state of the vibrational state to the excited state of the vibrational state. And all of you studied that in more details. So I'm not going into more examples or fun fact to that. You already know all those things. So this happens in IR. Then comes what? Then comes the UV visible region. Okay. Although I write visible on the right hand side, UV in the left hand side, but in energy wise, visible is actually low energy, then UV region. Okay. And UV-Vis region, we already know that 400 to 700 nanometer region is the visible region. And if you go below that 150 to 400, 300 or 400, it is the UV region. And over there, we are putting everything in electron volts. So I'm going to put that in electron volt. That actually comes around 1 to 100 electron volt, depending on you're looking at the visible region or in the UV region. If it is a UV region, it is close to 100 electron volt. If it is in the near to the IR range, near IR or red region, it is close to 1 electron volt. And what UV-Vis spectroscopy is actually connected to? It is connected to electronic spectroscopy or optical spectroscopy, as we talk about, because it happens in the region where we can see the things. So that's why it is optical. So what is changing over there in optical spectroscopy? We are changing the electronic distribution of the system. Okay, this is the reaction coordinate. So over there, we change the electronic distribution around the nucleus from one state to the other. So that is what we are changing in the visible region. And as we have already discussed, each of them is connected to a lot of vibrational states. So vibrational states, you can see the difference is much less. So that happens in the IR region, whereas this change from this one state to the other requires more energy. It happens in the electronic spectroscopy in the UV-Vis or ultraviolet visible region. Okay, so that is how much we actually generally cover. Now, instead of electronic state, now I want to change the nuclear state. So the nuclear state change happens in further right-hand side, somewhere around here to start with, where we change the nuclear states. Very similar to the electronic state, we are changing now the nuclear state. And when we change the nuclear state, we need more energy. And this energy falls in the gamma ray region. Okay, and this gamma ray region, where you heard the gamma ray for the first time, you remember when you're talking about the nuclear chemistry itself, that if I actually change the nuclear state or the nuclear combination, if I break them down or if I fuse them to create a new one, I create some energy, and that energy can come out as gamma ray or alpha particle or beta ray or beta particle, all those things. So gamma ray is a very strong energy. Okay, and this gamma ray is actually in the region of 10 to the power 3 electron volt or higher. Okay, it's a very strong energy. You can see it is way higher energy compared to the UV-Vis. So it is at least 10 to 100 times more concentrated in energy compared to the UV-Vis. So you need a hugely excited system to change the nuclear state. And you might be wondering where the X-ray falls. X-ray falls in between UV-Vis and gamma ray somewhere. Okay, so that is the full spectrum that we actually play with while we are doing the spectroscopy. As we are discussing last class, that we generally change the energy and try to find out exactly where the transition occurs. And as the different transition can occur at particular position for a particular molecule, because everything is quantized. Changes cannot happen in anywhere. It can happen only at a particular place. So the particular energy transition actually gives me the idea of what I am actually looking at. But before that, you have to look into like exactly what you are looking at. That is what you are actually changing. So depending on the electromagnetic radiation, you can control what you are actually changing. If you start with radio frequency, you are changing only the nuclear spin state flipping. That is NMR. Then if you go to the microwave, you can either change the electron spin state flipping or the rotational spectroscopy. Then if you go to the IR, that is the vibrational state we are actually changing. Okay, so that is what is actually changing in the rotational spectroscopy, vibrational spectroscopy in the FTIR region. Then you can also change the electronic state itself, and the electronic state change happens in the UV visible region. Again, you can connect that. Electronic state change means you are changing the how the electron is actually orienting all around the nucleus or the surrounding. That is the electronic state change. But if I keeping that same, only changing the spin, that is the ESR or EPR. Okay, so the relation between EPR and UV-Vis is exactly similar, what is the relation between NMR and the Mossberg spectroscopy or the nuclear state change. Okay. And if you go further down to the right hand side in the energy scale, we can even put enough energy to change the nuclear state. So that is what happens in the Mossberg spectroscopy. So again, I will take a brief pause over here, and just to make sure that you guys are following that depending what I am going to change, I have to change the energy of the electromagnetic radiation. Okay, everybody understand what I am saying over here? Okay, no questions, so we'll go further forward. Now, in Mossberg spectroscopy, we change the nuclear state. Okay, so nuclear state transitions we are actually looking into. So now the question is, why do I care about nuclear states change? I mean, nucleus is sitting in the middle of the every atom, which is actually making all the molecules. It is rarely coming outside and interacting with other things. So why do I care about nuclear states? That is because we already know in the other way around that if there is a nucleus over there and there is an electron cloud around there, this nucleus is actually controlling how this electron cloud would behave, right? It is actually controlling the movement of the electron through this interaction. And that we already go around it. It is H psi equal to E psi. H is the Hamiltonian, which actually shows the system, like how the nucleus is actually affecting the electrons. And depending on that, the electron movement will be controlled. That is given by this wave function psi, and that will also define what will be the energy of the system. It is the old school Schrodinger equation. Over here, what we are actually looking into, how the nucleus affects the electron. That is we are more concerned about, that is we are more focused about. But at the same time, the electrons are also affecting the nucleus at the same time, right? If the nucleus is affecting the electrons are also affecting the nucleus. It is actually, as you say, it is a system, it's a symbiotic environment. If nucleus is affecting the electrons are also affecting the nucleus. So the goal was, if there is a change in the electron density, electronic arrangement, and all those things, that will also affect the interaction between the electron and nucleus. So subtle change in electronic distribution will affect its interaction with the nucleus. And that is I'm going to take a look into. Okay. So if there is a subtle change in the electronic distribution around my nucleus, can I actually detect it? And that I'm trying to detect by changing the nuclear state itself. Okay. So what I'm actually trying to do is the following. So over here, if I want to see a particular change over here, I have to first create a gamma ray. Okay. So that I can actually change one ground state nucleus to the excited state nucleus. But gamma ray is not that easy to produce. It is not as easy to produce as a simple optical spectroscopy, like I turn on a switch and I turn on the light, because that is much more lower in energy. But gamma is very high in energy. So first I have to create gamma ray first, so that I can excite a ground state nuclear state to excited state nuclear state. Okay. So how to create a gamma ray? Anyone? So I want to change a ground state nuclear state to excited state nuclear. So for that I need a gamma ray. How I can create a gamma ray? Anyone?
We can take a radioactive isotope of an element.
Very good.
And
so if I take a radioactive element, that can give me gamma ray.
gamma
But what
ray
is the change? And what is the change happening in the radioactive element itself? Why it is leaving gamma ray?
Electron capture.
Electron transfer. We already just discussed. Electron transfer is not going to give me the energy in the gamma ray region. It is in the UV visible. you said electron capture. Okay, electron capture happens